Okay, I think we are ready to start with the last talk of today by Paolo Di Vecchia on waveform from unitarity. Please, Paolo, 45 minutes, I'll let you know.
Yeah. Well, let me thank the organizer for inviting me to talk. I want to talk about the waveform from unitarity, but I want to warn you that this is very preliminary. Most of the calculation we have done more or less during the workshop, and the first comparison with other paper we have done yesterday. But let me start with an introduction. So first of all, what I'm going to say is based on 3 papers with Carlo, Rodolfo, and Gabriele. And so if you want to compute classical quantities at the deflection angle in 3 p.m., you need to extract the classical part of the two-loop amplitude. And in particular, one needs to compute the integrand of the classical two-loop amplitude that up to a few days ago was only known for the conservative part of the amplitude, coming from this paper, which is already 2.5 years old, from C and collaborators, and confirmed by the paper by Raphael and Gregor and Liu, and by Solon and Choing. So the integrand of the conservative part of the amplitude was already known since 2.5 years, but we will see that the complete integrand is only known now. Once you know the integrand, then you have to compute the integral, and this is can be done by writing the integral in terms of master integral, and then can be computed in terms of differential equation. However, the final result for the conservative part of the classical amplitude had a problem that the deflection angle was divergent at high energy. And this was, of course, consequence of the fact that the real part of the classical amplitude was itself divergent at high energy. And this was in contradiction with the results of Amati, Ciafaloni, and Veneziano in 1990, based on unitarity and analyticity and crossing symmetry. Then there were many months in which people start to discuss why there was this discrepancy. And after infinite discussion on the origin of this problem, the only way to convince people was to do the calculation in massive n=8 supergravity, approximating the integral in the soft and not in the potential region. And then in this case, one sees that the problem disappears if one adds to the conservative piece also the contribution of the radiation reaction. But how to compute this extra piece in GR is the classical integrand of two-loop was not known. Now, from the loss of angular momentum, Thibault computed the radiation reaction contribution to the deflection angle that added to the conservative part eliminated the problem that we had at high energy. And this was without knowing the complete classical part of the two-loop amplitudes. In this talk, I will present an alternative approach, which is based on unitarity, cross symmetry analysis, that allows to compute the radiation reaction, again, without knowing the complete classical two-loop amplitudes. It's still not clear why, from a physical point of view at least, why the 2 previous approaches give the same result. On the other hand, at this point, there is no doubt that they correctly complete the conservative contribution of the classical amplitude, as shown in this very beautiful paper by Niels, Paul-Henrik, Ludwig, and Pierre. And I look forward to hear the talk by Ludwig. So they managed to compute in a very simple and intuitive way the complete classical integral, including both the conservative and the part due to radiation reaction. Then from it, they derive in a unified way the previous result obtained instead with different techniques. In this talk, I will briefly describe our way of computing the radiation reaction effect in GR. Then I will show that our approach also allows to compute the waveform in a rather simple way. And our approach is based on the calculation of the three particle cut from the unitarity relation. The three particle cut becomes to be relevant only at 3 p.m. And the fact that an intuitive way to see that this connected to radiation reaction is due to the fact that the three particle cut has an intermediate graviton exchange, and that's the reason why in this way one gets radiation reaction. And I will perform the calculation in parallel in n=8 supergravity, massive supergravity, and in GR. So this is the three particle cut. So these are the 5-point amplitude, the classical 5-point amplitude that appears in a unitarity relation. Here I use in n=8 supergravity, the indices are 10-dimensional, and the sum of the polarization is done in this way, while in GR they are 4-dimensional, and you can do the sum over the polarization using the Donder propagator. And I don't need to symmetrize here between mu and rho and nu and sigma because the amplitude is symmetric. Here the integral is done in 4 dimensions, but in order to cure infrared dimension, I put d, which is close to 4. And this is the 5-point classical amplitude that has been computed in these 3 papers. And with different technique, we use string calculation and performing then the field theory limit. This amplitude, it's also transverse, satisfy this equation. And in this amplitude, we should separate, for instance, if we consider, this is a picture that describes the previous 3-particle cut. So we have P1 and P2, and then P3 and P4. We have the longitudinal and the longitudinal direction, which are the R direction with this, and the transverse direction, this is in the bright frame, are the soft direction. So if a soft direction appears sum to an R direction, is neglected in the classical limit. And so, for instance, in this, the amplitude is constructed taking essentially neglecting contribution. So Q1, Q2, K, and also Q are soft quantity that can be neglected when they are summed to the hard quantity like energy or P bar. So in n=8, it's convenient to choose the following 10-dimensional cinematics. So we are in 10 dimensions. They are massless, but they get a mass from the compactified direction. In GR, all the momentum are 4 dimensions. And in the amplitude, there was a quantity beta that in the case of n=8 is given by this expression. Instead, in GR, you have to subtract the contribution of the dilaton. And so you have to distinguish between the 2 cases. Then using momentum conservation, So you have in the amplitude two d delta function, but two of them are in the time direction and in the longitudinal direction. And then we can perform the integral over this, using this two delta function, one can perform the integral over the longitudinal direction of K1 and K2. And doing that, one gets a Jacobian that cancel the factor K0, 1, and 2 and produce this extra factor. And so the three particle cut becomes this now, where instead of using integral over K1 and K2, we integrate over Q1 and Q2 here. And there is actually one of the integration can be performed because of this delta function. And notice that Q1, 2 have longitudinal and transverse and time direction, which are all soft, exactly like K, unlike P1 and P2. So in the classical limit, as I say, we can neglect the soft part. So K1 left is just P, K2 left is just minus P. These are the energy. So this Jacobian becomes 4EP. And then one can treat the two 5-point amplitude more symmetrically by introducing Q3 and Q4, which appear in this expression here. And notice that Q2 plus Q3 is also plus P2 plus P3 is 0. So this Q2 plus P3 essentially is Q, and the same for Q1 and Q4. So you introduce this relation, and then you can integrate over also Q2 and Q3, introducing this delta function. So you put everything together, and you get, you go to impact parameter. So from the imaginary part of the three particle cut, you got imaginary 2 delta 2, and you get a product of a term which is an integral over Q1 and Q2 containing the 5-point amplitude, and a term containing integral over Q3 and Q4 containing the other 5-point amplitude. And the Q is written in terms, in this combination of Q1, Q3, and Q4. And so they are separated here and here. So this is the basic expression that we want to use. And the previous expression is very powerful because it allows to compute the imaginary part of delta 2 directly from unitarity without needing to know the complete two-loop amplitude and then extracting from it the imaginary part of the diagonal. The previous expression can be written in a more compact way, like that, just in terms of the impact parameter transform of the 5-point amplitude. And the sum in GR is over the two graviton polarization in n equal 8 is over all massless degrees of freedom. So graviton, dilaton, vector, and scalar. Now, this was also the starting point of the paper by Amati, Ciafaloni, and Veneziano. In 1990, they computed the imaginary part of 2 delta 2, plugging in this amplitude the double Regge limit of the 5-point amplitude. So the double for a 5-point amplitude, one has five Mendelssohn variable, 3 energy and 2 transfer momenta. You do the double Regge limit is done sending the 3 energy to infinity, very large, keeping two energy with respect to total energy fixed and keeping the transfer momentum small. In this way, the amplitude simplifies, so you can insert the amplitude here, and after some calculation, they manage to compute the imaginary part of 2 delta 2 that turn out to be divergent as log S. That was the major result of that paper. And then using analyticity and crossing symmetry, they managed to deduce also the real part that was instead finite at high energy. And that was the other important result of that paper. And that gives a finite deflection angle. So that is the result obtained if you put a double Regge limit. What we have done instead in one of the papers mentioned in the introduction at the beginning, we have considered the massive case, and for the amplitude we kept only the leading divergent term when the momentum of the graviton goes to 0. So this is the leading soft term of the amplitude. And in the soft limit, this term is much simpler than the total amplitude. It's just a product of the soft factor here times the 4-point amplitude without the graviton. And then you can insert this amplitude in the previous expression, and in this way we computed the imaginary part of 2 delta 2 in gravity, obtaining this expression. Then we use again argument based on unitarity, analyticity, and crossing symmetry. And then we notice in n equal 8 that the amplitude could be written in this form. So there was a term which was infrared divergent here, which was accompanied by this log, some log the velocity when you are in a threshold. And then the real part was connected to the imaginary part by eliminating this factor here. And then we thought about it, and we argue actually that this could be more general than just n equal 8. And in fact, the two imaginary terms here and here come from the 3-particle cut integrator over omega from 0, and that gives the infrared divergent up to a cutoff, which is essentially this one. And then real analytic, and then for sigma between -1 and 1, you can use real analyticity, and the amplitude must be real. But when you go to the physical region of the S channel, essentially from 1 minus sigma square that you get for a real analytic function in the region between the two cuts, you get an extra term here that gives the real part. And in this way, we extract the real part from the divergent part of imaginary delta 2 and finding in GR agreement with the Thibault result. If we want to use the complete amplitude, instead, the integral cannot be done, and then we have to go to the technique of the differential equation and master integral. We have done this in our last long paper, and this is the expression we arrived to. Notice that this term has precisely the divergent term, which is the one that is obtained putting only the soft term of the 5-point amplitude. The term with the log of sigma square minus 1 has the same coefficient as 1 over epsilon, as argued from the argument before. And if you take the limit of large energy, you get a log S. So the log s square cancel, and in the end you get log s in complete agreement with Amati, Ciafaloni, and Veneziano. And I should also mention that the divergent term agrees on a recent paper by Carlo, where I use infrared exponentiation into space, getting the same result. And then if you include the radiation reaction part to what was known in the conservative region, you get these two extra factors here, while the black factors were known from the potential, from the conservative part. And you see that adding these two terms, you get something which does not diverge anymore for large energy. If I don't integrate over the momentum of the graviton, we can get also the differential spectrum of the number of emitting graviton according to this formula. And that, because of the factor h bar, is divergent in the classical limit. If you multiply this with h bar omega, the h bar cancel, you get the differential spectrum of the energy, which is like that. And then if you integrate over the momentum, you get the total energy. We have done the calculation of this expression, reproducing the result obtained by Enrico, Julio, Michael, and Mao. So let's come to the waveform. The waveform is just taking one single factor of the expression that we have in imaginary part of delta 2. And when I to integrate over delta, delta is this combination, and the combination with plus is k. So what we have to do, we have to perform the integral, transforming all the Q1 square, all the Q1 in terms of delta and k. And then you have to perform this integral. And okay, I have only one delta function because I've already performed the integral of the delta function that was originally in the amplitude. And in particular, for I plus n times, I'll get the two polarization of the graviton. And in the following, I will discuss in detail the case of graviton in GR, but the same procedure can be applied for other massless state, as for instance, the dilaton, as we have done in our published paper. So the starting point is the 5-point amplitude for the graviton emission in classical limit. This is the amplitude, and there is again this beta, which in gravity is this one. So we take all outgoing momenta, and again we have the hard component and the soft component for P1 and P2, and this is the way we write K, and the space part of K, it can be written in terms of the two angles. And then we have to write the two polarization, which are orthogonal to K, which are E phi and E theta. And the waveform, the two polarization, are computed by saturating the amplitude with these combinations. Now, in this equation, we need to do the integral of denominator like Q1, Q2 square. And so we need to know to do how to compute this integral. But this Q1 and Q2 square have not only a transverse part, but have also a longitudinal and time part, which are also soft, cannot be neglected. So we have to compute them insert into integral and compute the integral. So let me just sketch here what we do. So this is the transverse part of Q1 square, and then I need to explain to you how to compute the longitudinal and time part, but accept these two formula by now. And then when we insert this formula in the original expression, because of the kind of mass term here, so this propagator is a massive propagator, and so we get a modified K0 Bessel function. If we have this term upstairs, again, one obtain this equation, and for the product of two, you can write in terms of K1, but there is an extra integral to be done. And now this integral contains these quantities C1, C2, D1, D2, and they can be computed by imposing a conservation of momentum along the time in longitudinal direction. And this exact mass shell condition, essentially, if you write a mass shell for K1 square and K2 square, you can rewrite in this form. And you see that this is as a soft term, this as a soft term square. So this can be neglected in the classical limit. So we get these two equations that we have to solve. And you can solve either in terms of the rapidity. So we write the longitudinal time component in terms of the rapidity of P1, P2, and K. And I mean, if you go through the calculation, you get Q1 left, Q1 longitudinal, and Q1 0 by these formulas. And using this formula, you arrive to the complete expression in terms of rapidity, but they can be also rewritten in terms of sigma, cos theta, and the two masses, and they are given here. So anyway, these are formula that complicated formula. If you plug all this formula in the waveform for the time part, this is the final expression that we get in terms K0, K1, where this combination here is given in terms. I mean, everything is function of B, K, omega, if you want, the two angles, and sigma, and the masses. So this is the waveform in the frequency domain. If you integrate over the frequency, one gets the previous amplitude in time domain. And for doing that, you need this formula for K0, and from this formula, you can derive also the other for K1. So you plug all this formula in the previous expression, and you arrive to this equation here. And now, and so what it remains to do here is the integral over x. We have not done explicitly, but this can be done using, one can see all the integral of this form, and you can perform the integral in an explicit way. Now, if you take the previous amplitude and you take the limit where u goes to infinity, you see that this term goes to as 1 over u square. This term goes as constant in u, and this term goes like 1 over u cube and this goes 1 over q squared. So the only term which you can give a constant term or a term which goes 1 over u is this one on the third line. So for u going to infinity, the leading term of the waveform times in time domain goes as a constant, and the next leading term goes as 1 over u squared. The constant term is the memory term that in the frequency domain comes entirely from the leading soft term, omega going to 0. And for this waveform, one can see that the term which goes 1 over u cancel, so there is no correction to 1 over u. So for this waveform, we can only extract in the going to u going to plus or minus infinity, the memory term. And we need to compare our result with that of other authors. We compute the waveform that we had in the previous talk. Essentially, we managed to make a comparison with this paper. However, the problem for comparing with the paper is that they write the expression in the center of mass system. In the rest frame of one of the particle, while we have the expression in the center of mass system. For the memory term, we managed to go back to the original expression and write the term in a Lorentz invariant way. And so we can go from our center of mass to the rest frame. And we compare the memory term that we obtain with the memory term in this paper, and we find agreement. We can also compare the memory term with the paper by Sen and collaborators, and that is written in the slides of Ashok Sen talks. And the term that goes as a constant in memory term reproduce the term A mu of Sen talk. Why Ashok wrote also the contribution to B and C, which are not present for this waveform. And our expression for the memory term can be obtained from A mu that Ashok wrote by restricting to the case of two-particle elastic scattering and choosing the momenta. These are the momentum of Ashok slides here. And these are, we have different, we use all momentum outgoing. Instead, Ashok use a different convention. But if you use this relation and you use also the Q is given by the leading icon by this formula, you insert this expression in A mu that Ashok Sen wrote, then you recover our result. So in conclusion, the waveform for the time for the X component, from our calculation, you can extract the memory term and only, but the contribution of B and C, we have to compute the other polarization, the waveform for the other polarization, and that we are doing, but we have not yet finished the calculation to compare with the other paper. Now, I want to finish my talk going back to the imaginary part of delta 2, and I getting some inspiration from Bloch-Nozick, and this calculation reminds pretty much the
爸爸在看视频。Sorry.
Mute yourself.
Yeah.
Thank you. Go ahead.
And the formalism that here I will develop is pretty much similar to what Ricardo was talking about in the beginning of his talk. And let me say that I learned about Bloch-Nozick. My master thesis was written in 1965 and dealt with Bloch-Nozick methods. And my advisor was Bruno Tuschek, who was an expert of infrared divergent. And at that time, the first storage ring in Frascati was constructed. And actually, in 1963, they detected the first collision, observing the Bremsstrahlung. And then there was in the process of updating the original storage ring. It was called ADA, which in Italian means anello di accumulazione. And that was supposed to be upgraded at the end of the 60s. And the upgrade was called Adone, because it was a big ADA. And at that time was very important to see how the infrared divergent cancel in QED process, which were very relevant to understand what came out from the storage ring. And that's why Tuschek and the group in Frascati working in that period on infrared divergence. This group included Lia Pancheri, Giancarlo Rossi, Mario Greco. And actually 65 was the same year that Weinberg was computing infrared divergent, cancellation of infrared divergent in gravity. However, there was no communication between the two things. Now, if I go back to the imaginary part of delta 2, there is the contribution of the 3 particle. So this part comes from the contribution of the 3 particle cap with emission of the graviton. So although the elastic amplitude has no graviton, external state, the imaginary part of the elastic amplitude knows that the graviton exists. And so this strongly asks us to include graviton degrees of freedom in the iconal. And let's see how this problem is solved in the Bloch-Nozick model that describe the emission of soft photon from an elastic scattering of 2 massless particles. The photons are soft, and therefore the fact that they are emitted doesn't modify the elastic process. And what I'm saying for photon can be trivially extended to graviton. So let's work on the Coulomb gauge, where I have a 0 equals 0, and this for the space direction. And then the most general solution of the free equation is this, where A is a space index. If I include an external current, then I have to solve this equation, and which is given by, formally by, this is the solution. But the solution depends on the choice of boundary condition. But if we compute the solution, we can introduce the in and out field. And the solution that is relevant for us is A retarded, which goes to 0 for t minus infinity. And then the solution can be written by A in plus A retarded. And plugging in the explicit expression for A retarded is given by this in terms of the current. And for t going to infinity, you get the A out equal A in plus A retarded. But this expression contains oscillators, but this expression is C number. And the S matrix is defined by this way, and you have to compute the S matrix which satisfy this equation. This is pretty much also what Ricardo was telling us in his model. And the solution is this, which is unitary. So if you do S as dagger is 1. So if you use so here you have an exponential with both creation and annihilation operator. If you use the commutation relation, you can separate the two exponential, but you get an extra term. So if you start from the unitary S matrix and you normal order the harmonic oscillator, we get exactly the term which has the same form of the imaginary part of the diagonal at 3 p.m. And then from this term, we can compute the probability that in the elastic scattering, no photon is emitted. So you saturate with a vacuum, you get this. The probability that one photon is emitted, you get this. The probability that n photons are emitted. And if you sum the probability, you get 1. And actually, they satisfy a Poisson distribution where n bar is the average number of photons emitted. But all this is valid if the photons are soft, and therefore they don't influence the part connected to the elastic scattering. But if they start to modify, if they start to have enough momentum, they will modify the elastic scattering, and one cannot treat the two, the elastic part and the photon emission separately. And the question is, how is then the S matrix modified? So if we go back to our problem, how is the diagonal modified if you include the degrees of freedom describe the graviton when they start to be no soft? So this is the problem that I think we have in front of us, and hopefully this will be solved in the near future. So let me come to the conclusion. By now, at 3 p.m., we have a very good control of the classical amplitude of the classical observable. We would like to understand in a more physical way the contribution of radiation reaction, and in particular, the two approaches that give the same result for the scattering amplitude, why are equivalent. We have to finish the computation of the waveform and compare with the result of other authors. But in front of us, we have definitely the 4 p.m. We have already the conservative part here. So the question is, how do we get the rest? Do we have to go the hard way, or can we find shortcuts as at 2 p.m.? Okay, thank you for attention.
Thank you, Paolo. Thank you for being on time. So we have time for questions now. Please raise your hand or just, speak up. Unmute yourself.
Donald.
Hi, Paolo.
Hi.
So let's see, there's some feedback. Try again. So in this KMOC formalism, there's a nice match between the radiation reaction and this impulse. So I guess there's a sort of separation. There's some conservative bit, and then there are some terms which involve the cut. So those cut terms, there was a nice thing about them. That, it was a bit like an event shape there's some decoration of the loop integrals if you want to compute the change of momentum of one particle compared to another particle. But when you add them up, you get the change, you get the stuff dumped into the radiation. So you can really see the radiation reaction sort of matching with the, the failure of the or of the non-dissipative part. What do I say? Of the dissipative part of the impulse. Yeah, so just a comment. I mean, I think there is sort of a physical point of view on, how these things fit together from that perspective. You can also see the relation to the waveform. Yeah.
So just a comment on that. Like I'll say more about, or we'll say more about this tomorrow, I guess. But it's not just the 3-particle cut, right? That includes radiation reaction pieces. There's like some other pieces in the other cut contributions and in the virtual as well that you have to take into account. Yeah,
it's a little hard. It's a little hard to completely separate them, but there's at least. Well, I mean, one thing you can see is that momentum conservation is just true, to all orders.
Are you sorry if I intervene? Are you referring to the 3 p.m. or to the 4 p.m. already?
It holds to all orders.
Huh?
It holds to all orders.
All orders.
It's just a property of the formal observables. So you can write them apart. You can write them in diagrams, but you can just prove it to all orders. There's some nice aspects of that.
Paolo, you want to?
I mean, so in some way, what are you saying that we don't need to understand the exponentiation? Is that what you mean?
No. I'm just it's just about the more this physical point of view. I think at least there's an intuition if you look at all these observables together about how the radiation works. Like Enrico says, it's not super clear. I mean, it's not like I can say, oh, that bit is radiation reaction, but you can see that the radiation reaction is completely encapsulated in the formalism. You can assure yourself that momentum is conserved to all orders. You can really understand the relation to, the waveform. The exponentiation, I think, is very interesting. I absolutely agree with you about that.
But I don't know if I mean, yeah, one thing is momentum conservation is obviously correct, exactly correct. But I mean, the precise way in which dissipative effects feed back into, say, the scattering angle is not such a straightforward thing. I mean, what Paolo described is, for instance, how at 3 p.m. we could relate this radiation reaction to a soft theorem our way, or, Damour did it in a completely different way with the same result. But if you go to 4 p.m., I mean, the situation is such that, as far as I understand, nobody has been able yet to find the radiation reaction, the full radiation reaction at 4 p.m. So, but we know some certain things. I mean, we know that, for instance, this the coefficient of this 1/epsilon conservative contribution to the scattering angle is the total radiated energy at 3 p.m. But, it doesn't look straightforward to me. Everything looks highly non-trivial. Maybe I don't see the simplicity that you see.
Yeah, maybe I'm, I mean, in this sort of approach we've been developing, there isn't really a sharp distinction between dissipative or conservative or anything like that. Mm-hmm. It's just the change, the radiation or the change in momentum, the scattering angle. It's just it comes all in one package. It gets harder when you start to say, oh, I'm going to this bit's there and that bit, And now, of course, if you want to do a computation, you might well want to break it up. But
no, actually, I'm all with you. I mean, in the amplitude approach, if you don't separate out regions, that's what you do. You'd get everything in one shot. But I thought what you meant is that it is simple to.
No. I think the hard bit.
Tangle the two things. Yeah. No,
that's not so easy. You can't sort of say, oh, it's just this diagram or that little bit there. At least I don't know. I'm sure.
Yeah. No.
Maybe my fault. But but when you put the whole thing together, there is a nice. Nice consistency.
Then I'm personally all with you.
Yes.
I don't know others.
I mean, maybe also one more comment to that. You can use KMOC. You don't have to compute KMOC in the full soft region. You can compute just a conservative bit of it. For example, we've done that. Then you can compute the full thing and subtract the two. Then you know exactly what is the radiation contribution. Alternatively, if you can just compute in the radiation region, then you just get the radiation contribution. So, there might be some more simplifications that you can do. Just a comment, you don't have to compute KMOC in the full soft region. You can focus on particular physics pieces that you might be interested in. We haven't done it, or no one has done it to just compute it fully in radiation. But
you cannot do that. The potential region is completely ambiguous and spurious and ill-defined. You need to include all the conservative part of the soft, or your answer makes no sense. And we are discovering that actually, and it's kind of nice. In fact, if you start comparing even observables with just the potential, you're going to find that the answer don't even match. Like the log of B, for example, in the potential is not there in the full answer. It should not be there. And if you're going to compare it to, say, to Thibault's calculation in post-Newtonian, you're going to get it wrong. I don't know if Mao and company compare, but it's off by a factor of 2. And the reason is because there's a lot of spurious contributions from the pole that Gabriele was mentioning, hidden order epsilon corrections. But the pole is unphysical. The pole will cancel out. So for us even to compare with them, we had to include a lot of spurious order epsilon corrections. And now we actually finally agree. But there is a lot of ambiguities, spurious finite pieces in the potential region alone, which are completely unphysical. They would all drop out, which don't allow you to do much if you don't include the conservative subpiece. So I don't think this separation makes any sense.
Are you talking about 4 p.m. or 3 p.m.?
4 p.m. There is nothing at 3 p.m. At
3 p.m. Everything is fine.
But that the separation is very clear because one is time reversal invariant, the other one is not. In that case, you don't even have to think. You can expand in velocity and be post-Newtonian minded, and you're fine. These guys go with VQ, VV, these guys go V squared. We are good. Now at 4 p.m., the V squared V4 have soft pieces in it. And you need those to make sense in the calculation or you get it all wrong. And this is something that we are learning slowly from the PM point of view, which I had not appreciated so much in post-Newtonian because the way we do in post-Newtonian, we expand, and then the cancellation that we showed with IRA, you can see from PN, it's all fine. But from PM, you start generating a lot of extra baggage that is gonna be subtracted from the soft region that if you don't include, I'm actually very curious, I don't know if Alessandra's here, how she managed to get a good agreement with numerics, because this log should not even be there and they shouldn't work at all. So this should be completely off the potential alone. I have no idea why they managed to get something close to the true answer. So it's something that we should definitely discuss because when you include the soft, a lot of finer pieces in the potential, we see them already, they're gonna go away. So this potential has no right to fit anything. So I have no idea why this worked out.
I don't know if Thibault is there. No?
Yes.
Oh, yeah, because you were telling me something similar by email. Do you want to comment on this?
Not now. I'm still absorbing what Paolo was saying and trying to think.
Yeah, no, I was referring to what Raphael was saying.
Yes.
It sounded very much like something you were telling me.
Yes.
But just a question, Raphael.
Yes.
I mean, at 4 p.m., there is an expression by by Zvi et al. In the potential regions.
Yeah, we just managed to get the same answer after adding a lot of spurious terms to the answer.
What he's saying is that
So the answer is completely unphysical, and I'm very shocked that it matches anything at all.
No, this looks very exaggerated. It matches the tutti frutti results.
No, but as you know, Thibaut, the log of J, for example, is off. It doesn't even match your 4pn angle. The 4pn angle, your log of J in the potential.
No, but this is for trivial reasons. Yeah.
Exactly. It has to cancel with the tail.
We know. This is trivial. We don't
Exactly,
learn.
but the comparison, it was made with the potential alone. That's what I understood Alessandra was doing. And that cannot fit anything. So I'm very surprised that can fit anything at all. If you fix it, then it works. Then I'm with you. But I understood they were comparing without fixing anything.
Yeah, but they suppressed the 1 over epsilon, and the agreement is much worse than EUB. EUB, which uses the log, works well.
I'm with you. But if they just subtracted the pole and nothing else and did not fix anything else, that should not work at all.
Maybe I can clarify something.
Yes.
Now I think people here like South region, and that's completely reasonable. But for me, especially for the application to binary dynamics, I think I would still prefer to separate into potential and radiation. And the reason is that when we apply this to a bond orbits, we can have a very good control about like what we're gonna use in the equation of motion. Like conservative goes to potential, and radiation reaction will treat them separately, even though for scattering you mix of them together, and like tail you also treat them separately. So I think for me at least, it's actually more useful in terms of potential plus radiation. But of course, the answer with potential itself is not the physical answer, as Raphael said, but in the sense that it gives you part of the answer, and we just need to come to the rest.
I'm trying to say, Cheshen, that it doesn't even give you part of the answer.
Yeah, but like for example, when Sandra made the plot, there's a choice about like how you have to deal with those 1 over epsilon, and how do you want to choose the scale and the finite part. So I think in Zvi's or Alessandra's talk, you'll see that it's preliminary. It's there. That word is there for a reason, because.
Okay, so they must have fixed mu and somehow fixed these issues of ambiguity somehow. But I would like to know how they did it.
The claim is not that it's unique, but it's a choice. So,
okay, but that is what Thibaut said. You can fix it or E or B it, and then it can obviously match. Then it'll be fine. But by itself, it cannot stand. It cannot hold water. In fact, we'll show, Gregor will show the answer, and you'll see all the spurious terms that are in there that they should not even matter.
Mm-hmm.
There is Mao ask.
Who?
Mao.
Hi. Yeah, just a quick comment on the 4pm. So the scale mu was chosen to minimize large logarithms. So the mu is chosen to be equal to Q or 1 over R. So and if you want to do it in a more fine-tuned way, you can also include the square root of V factor, but that doesn't really matter when you look at the last few orbits shown on that plot. So there are some reasonable choice of mu included, and more crucially, it was tested with the post-Newtonian result. So the 4pn result, if you only take the potential part, ignoring the radiation part, it actually fits the curve quite well. So for some unknown reason, the radiation part was subdominant, just a few %, even in the post-Newtonian result. And we extrapolated to the post-Minkowskian result, and the result happens to fit the curve very well again. So that's a little bit of motivation.
We can get back to that, because the potential part has a lot of spurious contributions that should not be there. So I don't know why it worked.
Oh, okay. And yeah, just one more comment. The potential region is not well defined, it's divergent, but our definition happens to agree with NRGR For example, with the calculation by Bloomline, we agree with the 6pn part, including both the pole and the finite part. So yeah,
that's fine. Yes, that's fine. But that potential part is also not physical. It needs the soft piece anyway.
Okay. Okay.
There is a comment by Justin Vines to everyone in the chat. The one plot that was shown by both Svi and Alessandra was made simply dropping the whole 1/epsilon term, not keeping any log from expanding in epsilon. There was thus no need for a choice of mu. I'm just reading.
Wait, so you drop the mu? You can talk. Did you drop the log of mu too?
There was no choice. Yeah. Not keeping any log from expanding in epsilon.
You didn't keep any log whatsoever.
That's correct.
Ah, okay. Then you didn't just subtract 1/epsilon. You removed the whole thing.
Yeah.
Ah, okay. Now I understand, because it's off by a factor of 2. So if you kept it, you would have gotten completely wrong answer. I see. That's cheating. Okay.
Well, it was just the simplest choice.
Sorry?
It was just the simplest thing to do.
Yeah, I understand. I'm surprised that it worked. I'm very surprised that it
We
worked.
are also surprised that it.
Because as you will see tomorrow, no, on Wednesday, when Gregor shows, because we match now SV's result for the SV et al. Results for the potential, that there's a lot of other epsilon terms that we need to include to hit the pole to get the same answer. All of those are going to cancel with the tail. So they should not be there and they should not matter. So I'm very surprised that that works well at all.
Okay. Looks like there will be some interesting discussion on Wednesday. So any other hands? Trying to go through.
Maybe I can ask a question directly to Pablo's talk.
Yes.
So in the second part, you show the Bloch-Nordstrom approach. Can you say which part of that depends on, relies on the photon being soft? Because, for example, the part that's on the imaginary part is given by the 5-point amplitude square. I think that's also the right answer. So can you say which part of the derivation depends on the soft photon?
I mean, you have to treat, you have a current generated by the elastic scattering, and this current is given. And then you compute the probability of emitting soft photon given this current. But if the photon is not soft, it will change the current. So you cannot apply anymore. You cannot, you have to solve all the equation together. You cannot just give the elastic and determine the emission of the photon. If you emit an hard photon, it modifies also the Laxi scattering.
Now I understand. But it's a little bit surprising that if you replace the current in terms of the full current, then the answer will still be correct in the end. That, so in the sense that the imaginary part of the phase is the 5-point amplitude square.
Perhaps Yashen's question, Paolo, is how soft is soft? In other words, in the classical limit, if you want the graviton or the photon is always softer than the hard particles. So I think the question is whether Bloch-Nordstrom works beyond the Weinberg limit or not. Is that the question, or maybe I misunderstood?
Actually, not. But I think I understand Pablo's answer now. But just it's a bit surprising that the answer is still correct in the sense I replace the current as the full current, not just in the soft limit.
Yeah, but it's a full classical.
Yes.
Field.
Yes.
You see, that's what I mean. Maybe classical limit is enough. Doesn't have to be soft in the sense of Weinberg.
I would disagree because I think in the classical limit, the momentum transfer is also soft. So I think for that derivation to be applicable, the photon, the graviton has to be much softer than the momentum transfer.
Yeah.
Yeah, I think that's right.
Gabriele, I think, I mean, another answer to Paolo's concern and your concern is it's the same validity domain as the linear response formula I use, you know, that actually you can use this approximation where you compute the angular momentum loss by a conservative motion where you neglect the reaction, but you can use it back still to compute the effect on the scattering angle due to radiation reaction. So it's soft as long as this is a higher power of G than it's G cubed, finally, the effect on chi. And so expanded in G, this is small compared to the basic scattering angle you want. So being classical is not enough. You still need to be small compared to something else classical.
Yeah.
Okay.
Yeah.
In QED, you can compute, for instance, a Bremsstrahlung in QED, and you will get a function of the frequency of the photon emitted. Now, using Bloch-Nozick, you reproduce only the divergent part, the omega over omega. You don't reproduce the rest of the dependence of the omega. You see what I mean?
But is it because you use a certain approximation, like you know, like the photon being emitted only from external particles? I mean, for instance, do you get also the subleading soft contributions?
And I have not tried, but what one does, one writes that there is an incoming current, so a particle which moves with a certain momentum, and then at time zero, so for time less than zero, there are some, it's a bit what Sen does. So at time less than zero, there is certain momentum, and at time bigger than zero, there are other momentum. And since there is, if the particle do not move, then there is no radiation. But if you have difference in velocity between time less than zero and time after bigger than zero, then this produces radiation. But doing that, you recover only the leading soft.
Well,
I don't know if you can reproduce also the next to the leading.
Sen does also the subleading, for instance.
Yeah, I think there's an interesting hierarchy here, right? Between you know, if you just want to compute classically, you know, what has that got to do with soft, right? So, but they're locked together. So if you want to compute to some PM order, then you also need to go to some n to the soft order, and there's a relationship between these. So I mean, I think for the calculation that you were discussing, Paolo, well, I'm not completely sure, but I think you certainly need to go to next to soft. I think next to soft is sufficient to this order, basically for the reasons that Thibaut said. But if you want to, you know, if you were to compute at higher PM orders, then you would also need to compute to higher orders in the soft expansion.
Well, another way of saying what I say is that in the Bloch-Nozick, you have this exponential. Now, if you include the next to the leading, do you still get an exponential? This could be a question to answer.
This is the question. Yeah, I think I agree. This is the question. I don't know.
Yes, and probably one should try to do this calculation to see if you can also get something which exponentiate with the next to the.
Yeah, you correct your coherent state.
If I can comment on this, so for the subleading soft theorem, there are these subleading dressings, and they are closely related to the subleading soft theorem, and recently discussed. And I mean, yeah, that's also some kind of resummation. I think what you show, Paolo, relies on statistical independence of this photon emitted, so that there is no back reaction at all. So
Yes,
it's purely
yes,
elastic and there is
yes.
no back reaction.
Yes.
As soon as you start back reacting, you can start also to change the probability of emitting photons, and that will change slightly the distribution. I know some people are looking at that in strong field QAD and found some interesting results, but yeah, that's different.
But can you do that in your model? You had a model which is very similar to Bloch-Nozick.
No, but in my model, the current was fixed, right? Was the source was fixed, like in your model. It was exactly the same, actually.
Same.
So yeah. So but at the next, and then I mean, there are some works on subleading soft dressings, but I don't know how much they are related to subleading soft theorem. But okay, at first they don't include the log omega term, I think. They are working at 3 level, and therefore there is no log. Yeah, so and also, I mean, there are a lot of open questions on that. But I believe there should be some operator in the space of soft gravitons, and yeah, I don't know about this imaginary part of the conal, but there should be an operator on in the space of soft gravitons.
Yeah, it's a very interesting issue, I think. Yeah. Okay, well, we went a little over time, but never mind. If there are more questions, we can go on. I don't see any. Okay. If so, we thank all 3 speakers again, and we will reconvene tomorrow.